But anyway, we have some people coming to show you and give you an example of what we can do remotely. That's one thing. And then the second thing is to showcase, how we can look at objects at a really small scale.
Yeah, so I'm Dr. Ryan Nickel. I'm an electron microscopy manager down here at UC San Diego. My goal for the next 30 minutes is not to teach you how this microscope works, but it's to show you what you can do in your classroom and get kids involved. So I'm sitting right beside, if you can see my video, I'm sitting right beside a $500,000 electron microscope. So hand for scale. This is a vacuum system with an electron gun, and I've got lots of computers and fun stuff in front of me. And the whole idea here is that not only can I show you what this microscope can do, but you can actually control it. So you can bring it into your classroom, you can connect to it via the internet and look at what's inside. And that's what we're going to do for the next 30 minutes. I'm just going to have volunteers from the Zoom call. Who wants to control the microscope? And I'll talk you through it. That's how this is going to work. As we do that, as we have a participant playing on the microscope, you can engage and ask me questions if you do want to learn more about how it works. But the whole point is we want to show this capability. So we are not the only place to have this capability. We are part of what's called a RAIN network, which is the remotely accessible instrumentation network. There's a whole bunch of other schools and universities and establishments that have got various types of instrumentation available through the internet like this. So, thank you for the chat. Let's share the interface. So this is the user interface that you'll be able to access. This is a web page that you can access if you schedule with us. And we can look at all of the samples that's inside the microscope. So I've got pollen, shark skin, gecko, camera sensor, nanoparticles, MEMS, which is micro electromechanical system, which is it's actually a chemical sensor. It's on silicon, CD, tungsten wire, and a big bumblebee or bee. So who wants to go first? Who wants to use the system? I'll take the first response via chat.
Okay, Usha is interested, and then
okay.
Dustin, I think, was next.
Okay, so let's allow remote control. So who was first? Can you say it again?
Usha.
How do you spell that?
USHA.
Got it. Okay. So I'm now going to give Usha control. Have you got control?
How do I get that?
You should have got a request.
Oh, okay, got it. Yes. I have the option. Yeah. Okay. Okay, yeah, it says I can control your screen. Should I press on something?
That's a good question. So I'm looking at pollen right now. I'm not going to control the microscope from now on, but if you click anywhere on the screen in the video feed, you can move around actually. So you click somewhere. Yeah, that's how you move around. On the bottom of the screen, there are magnification arrows that allows you to change the level of zoom. If you look on the bottom left.
Yeah, I guess the font is a little too small.
Oh, okay.
Yeah, that's okay for me, maybe. No problem. Okay, maybe I can click on.
You can go somewhere else, yeah. If you don't want to do pollen, that's another thing.
Yeah,
so the whole idea here is that this is about a $500,000 microscope. It's what's used by real researchers. I'll help you zoom out a little bit. This is used by real researchers, and we can see down to the nano scale, which is basically a billionth of a meter. It's about 1,000,000 times better than an optical microscope. So you're looking at shark skin that we got from the Salk Institute right here on the West Coast. Go ahead and click somewhere further into the skin. Top left. That's the edge of the skin. And so not only can we give the kids remote control to fully use the system, I can also help out. So if I just help you focus this up just a little bit, and I can actually slow down the scan a little bit so we can get a really high quality image. you'll start to see it come through in more detail.
Yeah.
So an electron microscope, it's basically a souped up microscope. It uses electrons, but it's used in almost every conceivable discipline, not only from the very academic sort of chemistry, physics, biology perspective, but also more industrial vocational type of studies like mechanical engineering and those types of industries. Even textile industries use this. So it's a really high-end and versatile piece of equipment. And specifically at SDNI, we have developed some lessons surrounding sample sets. So we've got this sort of show and tell sample set. Feel free to keep moving around if there's something else you want to look at. If you're more interested in the biological stuff, the gecko's really fun. And we've also developed lessons around biology and various other disciplines. So if you zoom right in, yeah, right there. Can you see the arrows over here in the bottom left? If you don't, that's okay. I can help you out. Bottom left.
Oh, bottom left.
That's brightness. That's mag. So go the other way. Perfect. Keep zooming in. So these are the bottom up gecko's feet. They're not hairs. They're called setae or setae. And this is what allows a gecko to have its stickiness. So keep zooming in a little bit more. What we'll find is that these hairs break off into many, many, many smaller hairs. A human hair is about 50 to 100 microns in width. These hairs are about 10 times smaller, and they break down into 100 nanometer size filaments, as we'll see in a moment. So click the right magnification button again and to zoom in even more. Sorry, on the bottom left. Yeah. So zoom and focus are separate in an electron microscope. So that's zooming, that's one thing. So the controls just below the magnification is focus. So those arrows to the bottom left.
I think I need to let Dustin take over because I need to get my other pair of glasses.
Oh, okay, sure, no problem.
Sorry about it.
Sure, yeah, Dustin is next, and then we have Joanne will try after that. And
Thank
then,
you so much.
Yeah.
Not a problem. Can you just stop taking over? Let's see if I can.
What can I, do you want me to do something?
I think on the control bar, you can just say stop. Maybe I'm mistaken. Let me see if I can change this.
Okay, June is also want to try. Okay.
Okay, no, it doesn't let me, I don't have to do anything.
So I would say, okay, so maybe who was next? Dustin, can you go on the top screen and maybe see view options, and you could also request remote control.
I see. So
I think.
All right. I think I just
Stop remote control. I've stopped it now.
Okay, perfect.
Okay. So I'll see if I can.
Yeah. So,
all right. I don't know. I haven't pushed any buttons. I don't want to sabotage what you're doing.
No, push a button.
Okay.
So I just pushed a button and now I've just lost something. Okay, great. Okay. So let me bring this back up. So someone else requested control, but now I can't actually.
Yeah, sorry, I ruined it.
Oh yeah, it's all
I was signed into someone else's Zoom thing, so I changed.
Oh, is that you? Okay, I didn't want to give it over in case it was the wrong person. Okay.
Sorry.
Okay.
If I can just click approve, that would be helpful.
I know. So yeah. So what's nice is Ryan's system is actually just a web page typically, but because we're in this remote setting, it makes it a little bit harder. So the web page isn't working as well, but typically we wouldn't have to do a Zoom and it would be a much smoother interface. Yeah.
Yeah, I wanted to ask about if there's just a website that has all this data stored, and you could tell the kids, I guess, that it's, they're actually playing with it, but really I'm assuming it's simple just to have some sort of interface for them on the computer to go in and look around and have the scale there without having to actually use the machine in real time.
I mean, there are options for things like that, but we're trying to go a little bit deeper and to tailor what we're showing towards classes.
Yeah.
So that's sort of the goal. There are a couple of like Google Maps viewers things out there, but we're trying to give the real experience. And the real experience, unfortunately, does have some hiccups sometimes, but that's okay. Okay, I think we're good to go again. So which account are you signed into?
I just changed my name to Dustin. I don't know if that just made it even more confusing.
Oh, it's fine. You got it now. Okay.
Okay. All right. Let's look at nano.
Sure. This is going to be the most challenging.
Okay.
So these are really small nanoparticles. Let's go ahead. Can you see the magnification dial or the magnification buttons?
Yes.
Let's zoom out first, so left.
Okay. Should I use the double arrow or the little one?
That's fine. So what you're seeing is the sample is actually to the bottom left. You see the sort of lighter gray. So click that area.
Do I drag it? Oh, I see.
Just a single click. Yeah, you got it. So believe it or not, the samples are there somewhere. So start zooming in a little bit. And then what you're going to need to do, so that's fine. What you're going to need to do is
there a focus?
Is change the focus, exactly. So you'll see those features on the surface either get worse like that or get better if you go the other way. And right beside that, there's a finer checkbox. You can have more control if you click the finer checkbox.
I feel like I'm at the eye doctor. Is this better or worse?
Exactly. And I can always help out a little bit. This sample is actually quite challenging, but that's okay. We can.
Is there a way to tell what we're looking at? Besides, like, is there a label on there?
It just, so these are nano. It says it's a nanoparticle, basically. But we're not focused up yet, so we're at the point where. Yeah, I'm trying not to. I'm not doing anything right now. I want you to have the full experience. So keep going. I think you're going in the right direction. So you're starting to see maybe some, pepperings of features. That's not a nanoparticle. That's a bit of junk. See the smaller stuff? Yeah, that stuff.
This stuff here?
Yeah.
Ooh.
Go, try to focus on those guys.
Okay. Let me.
And so I guess one of the points that I always tell classrooms is that what we're about to be looking at and focusing on is completely invisible, not only to the naked eye, but to most other microscopes, general microscopes, optical microscopes that you might have in your classrooms cannot resolve this. It's fundamentally impossible to use those systems to see these types of things. So whenever you hear about nanotechnology and nanoparticles and nanomedicine, these types of things need an electron microscope. So you're almost there. If you keep zooming in, to those white blobs, those are actually groups of nanoparticles. That's not one nanoparticle. So keep focusing. And there's some extra settings that I might have to help you with, but if you keep focusing, you should get there.
This is amazing. It's almost like a race. I could see this being a race.
Oh, you're starting to see the sort of contrast in the middle there? You're starting to sort of get a hint of them.
Go back.
So I think your focusing is close, but not perfect.
Yeah, I'm bouncing around it. I think that's.
I wanted to add, Vicky had a good question that was, why is it possible to see anything in color? This is so cool. So, and I don't know, Ryan, do you want to answer that?
I mean, Angela, if you want to take a stab at it, I won't stop you, but I'll certainly.
I think you should answer. You're the expert here.
All right. I want to first of all address that we're almost seeing what. I want to help you out a little bit. This is actually the toughest sample to focus on. And I don't want everyone else sitting here looking at nothingness while I explain stuff. So I need to sort of really tweak some extra settings, which are a little bit complicated to talk to high school children about. So I don't usually talk about them. But there's some extra adjustments I have to make. So there are your nanoparticles.
Wow.
You can look at the scale bar and see that they're about 100 nanometers in size. Okay, so an optical microscope, you're looking typically at reflection, and different materials reflect basically different wavelengths of light, and you have a color sensor that allows you to decipher, make color images. That's sort of how our eye works as well. We've got different cone cells and so on. Rod and cone cells deciphering intensity and colors and so forth. In an electron microscope, what gives us the resolution? The resolution comes from the fact, broadly speaking, electrons are really tiny. You might have heard about wave-particle duality, that electrons are actually wave-like, so you can associate a wavelength with them as well, just like you might associate light with a wavelength. For all practical purposes, though, the wavelength of an electron is so small compared to anything you'd ever want to see. So we're resolving nanometers here. An electron's wavelength in this system is on the order of picometers. So nanometers is 10 to the negative 9. Picometers is 10 to the negative 12. We're using one wavelength of electrons. There is no dispersion. There is no color of electrons, right? But in white light, it's a mixture of all colors. The electron beam that we're radiating onto the sample is basically one color. And what we're seeing, in fact, I just realized I should scan a cleaner image for you. What we're seeing here is not what different types of colors are getting scattered off. We're just seeing if there's more or less electrons getting scattered from a given location. So in this area here, there's more electrons getting scattered for some reason, because the particle scatters more electrons and the background scatters less. So the detector in an electron microscope is not sensing color, it's just sensing how many electrons is coming off it. And a natural way to represent that data is on a grayscale. More counts is whiter and less counts is darker. I don't know if that fully answers your question.
No, I think that answers that. Ryan, do you want to switch operators? Or Dustin, can you hand it over to, I think the next person is Joanne?
Let's see here.
Joanne can request maybe? I'm not sure.
I could stop remote control. Is that
let's do that. Let's stop and then I can hand it over.
Okay, great.
That'll work.
Do I request it or do I wait for you, Ryan?
This is a good question. Sorry, who am I sending it to?
This is Joanne.
Yeah.
Sorry, what's the name?
Joanne.
Joanne. Yeah. Okay.
Does that work? Did you get a request? Okay, good. So you can go ahead and click a sample that sounds interesting.
I would like to look at a bee.
Let's
Very
do that.
good.
So we're zoomed in a lot right now. So you're going to have to demagnify and use the arrows. Yeah. So zoom out as far as possible. So you can see the wing. Click around and see if you can find something interesting. Like if there's anywhere interesting, to be honest. I find most people tend to go for the eye, if you can find the eye, but you're welcome to look at the wing or the hair or whatever else. So
this is currently the wing?
The top left of the image coming down to the bottom center is the wing, I think. I don't know what that side is yet. I'm a little bit lost personally. I'll help you out with the brightness here. I'll tweak the detector a little bit. Let me.
Yeah. So I just wanted to add to the color. So a lot of the times, so it comes out as a black and white image, but you can colorize it. So there's a lot of people that do false coloring. That false coloring is just someone who is adding color to what is, technically a black and white image. And then Amrit is asking, does that mean the darker bits on the nanoparticle are different from each other? Like the darker ones are different elements or something from the light source? So it could be, it depends. So what's tricky about research, I guess, is you kind of need to know a little bit about your sample ahead of time to figure out what you're looking for, because it's so easily, you can get easily lost, even with a bee that, we know pretty well, I think, overall. But generally speaking, the darker bits will be something that is made out of a different material. So different materials will contrast differently. If they're heavier.
I think this is the eye. I just wanted to point out, I think this is the eye here if you're looking for the eye.
Okay.
If you zoom in here and try to focus, you'll find it. Sorry, Angela.
No worries. So if it's darker, it will typically be something that's a heavier metal or heavier atomic element.
Other way around. I can add more.
Sorry. Yes,
I can add more technical detail if you want.
Yeah.
So there's a whole bunch of different detectors in the system. We've got really dumb detectors, which just say, oh, hey, there's some electrons. There's other detectors which can detect different types of scattered electrons. There's certain parameters that you can be sensitive to. So the detector that we're using now is one of the dumb types. And that's not to say it's not instructive. It just behaves more like you might expect a normal camera. There's like shadows that you can see, right? I don't want to get into that too much. It looks like there's perspective in the image. It looks like there's shadowing. So you can't really assign brightness and darkness to different elements in this case. But Angela is 100% correct that if you choose the right type of detector, You can then assign whether or not you expect more electrons to scatter off certain regions than others. So that requires sample specific information. So for example, if you have a heavier nucleus, you would expect that element to scatter more electrons. So therefore, the brighter points in that image may be attributed to a heavier element and so on. So the answer is not clear cut. It's a very difficult question to navigate, and usually requires a couple of lectures in undergrad. We can keep zooming in here, by the way.
Yeah, you should go deeper, Joanne. Go deeper.
I'm going to help you out a little bit because
Okay.
I really want to show you this. So I'm sort of focusing it up. I'll let you play around. We're going to start to see that sort of hexagonal structure. There's some coating and contamination on this, but you can start to see there's the hexagonal structure of the eye. There's probably a cleaner location. Unfortunately, this is a sample that's been used over and over again. But we're looking at, what's this, 20 microns, maybe a fifth of the size of a human hair. Maybe if I go over here, you'll get a better perspective. Ah, here, perfect. I don't want to steal your thunder. I really want you to play around, get a feel for how it all works. But you can certainly now start to see that hexagonal structure a little bit better. I can tweak this as well. I didn't mean to interrupt. Sorry, Angela. You can start to address the other.
No, that was perfect. That was perfect. And then, yeah, just to be cognizant of time, we have a few more minutes. So maybe, I know June was interested in trying at least, if we can squeeze another session in. And then after that, we have another demo. We have Marston, who is a colleague at Stanford, who's going to show you the AFM, which is a different technique.
I think I stopped my sharing.
Great. So who's next? Who did you say was next, Angela?
J-U-N. Good. Thanks, Joanne.
I also did undergrad at UCSD, so that was kind of exciting too.
Yeah.
So I think, yeah, you've got control, or you should have a request, and you can click a different sample from the menu on the right-hand side, or you can begin to navigate the bee a little bit more. It's up to you. So again, I want to stress that the sort of program that we're developing here at SDNI is we have show and tell. If you just want to teach your students about electron microscopy as a general tool, we can certainly do an extended session like this where we go into the science, a little bit more about how the electron microscope works, and allow the students to play around and explore the samples in a bit more detail, because usually we've got a bit more time than just 30 minutes. Or if you've got a very specific directed lesson that you want to try and achieve, we can also do that. We've had one community college teacher that was really interested in sharing and studying the different types of pollen that she had collected over the years. And what she would do is she would look at them under the optical microscope, and that only gets you so far. So we developed a lesson where we put in, I think, 9 different varieties of pollen and supplemented her laboratory class by first having the students look at the pollen under the optical microscope, and then she could then leverage this $500,000 instrument to go in a little bit more depth to show her students not just still images from textbooks, but to actually use the system live in her lab, exploratory. Hey, I think you did a good job. This is great. I think this is the wing, and I think there are actually little hairs on the wing that are actually, the perspective is a little bit weird, but all of these little dots here are actually hairs that are sticking up in different directions. So if you begin to focus a little bit more, you'll start to see them. Again, I don't want to steal your thunder. I do want to maybe move up to the edge. I'm gonna zoom out a little bit. The edge, often you can sort of see it a little bit better because of the angle. You can see the hairs on the edge of the wing here. Whenever you look top down, you don't get the perspective sometimes, so it's a little bit easier to see over here. You can still play for the last couple of minutes, and if there's any other questions before we hand over to the AFM.
June looks like he's very proficient at figuring out all the buttons. You're very fast.
Yeah, we're almost seeing all the detail here. And we're starting to see some interesting effects, which is another thing that we can go into if there's people interested in material science or electrical engineering. We can talk about why we're seeing this glowing. This is all to do with how the electrons are interacting with this non-conductive organic material. And this is another sort of problem or barrier that we have to surmount whenever we're using an electron microscope. Again, don't have a lot of time to really go into detail today, but that is an interesting lesson that we could explore.
Yeah, this tool is used by many types of people, like different types of researchers. So it's very broad. People from, organic medicine, electrical engineering, material science, chemistry, physics, applied physics, all sorts of types of groups or researchers would be working on this type of tool. And actually, the other tool that we'll take a look at as well. So what's nice is that these sets of tools can be used to characterize many different things. You just have to pick the right tool for what you're trying to look for and things like that. Oh, Vicky had a question on how long is the waiting list?
Well, right now, because of COVID, we don't have so many requests. Over the last month or two, we've maybe done a handful of classroom sessions. So if you get in touch with us, we are ready to go.
So, Ryan, did you provide an email address for them to contact us?
We have not. I was going to follow up with you and Angela after her program.
Sure.
Okay.
Yeah, and I put we're sending out the teachers a big long resource page, and I put the SEM sign up form on the link as a link for you to contact, for teachers to contact you. I mean,
Sure.
We had a question on how long does the session last? How many kids do you recommend at a time? Yeah.
So we do usually we do one class at a time, one period. So depending on how many people you have in your class, it can be 25 to 40 kids. And at the beginning, we just do basically pretty much like a potpourri of samples like we just did today. But eventually, it can be more focused on a lesson that you want to provide. So can I, Angela, put my email address on the chat room?
Yeah, please feel
That's
free to
probably
do that.
the fastest way to reach me. If you reach me directly via email, then we can follow up right away with scheduling with Ryan, and you're on the list. I can say that for the month of September, where when class restart, we are pretty open. So if you want to put that in your schedule, it is availability should not be a problem for September and October. So let me put my email in the chat room.
Great. Yeah, thank you, Yves.
Sure.
All right, so yeah, we're on the gecko foot. I recognize the image, looking good.
I mean, the thing that's spectacular that I always have to point out is this. If you go into the very end where all of the hairs like bifurcate and then they break off, you're talking about sizes that are 100 nanometers from a natural sort of living organism. These little pads, which, anyway, sorry. That's what I teach the kids. Getting excited.
No, keep going.
I think I've run out of time though, but I'll be happy to answer any questions. And then if there's any last second things, I don't want to hold up your program, Angela. So
no worries. Yeah. All right. So I think that about does it for Ryan. Ryan is really great. Yves is also really great. So just as a reminder, Yves' email is in the chat box. And then if you missed that, there's also the link to that information. Also, it'll be on the resource page as well. Oh, one question Yannette has is, do you have access to view viruses?
That is a good question. So no, one, we don't have viruses, but two, preparing biological specimens are very difficult. A bee and a gecko's foot is very simple, but whenever you get to like cellular materials and these types of things, they're very difficult. I think we've got some synthetic viruses that we can look at, and we've got some cells that are prepared by someone else, but we can't arbitrarily take anything and say, hey, we can show you anything. We have a very limited amount of those very specialized samples. We've got some, I think, brain cells and liver cells, and I think some synthetic viruses, but they're so hard to prepare. It's not my area of expertise.
Mm-hmm. Great. All right. Well, with that, yeah, thanks. Let's thank Ryan again. I think it was really informative and helpful and fun, hopefully.
I'm
Yeah.
having fun.
Okay.
All right.
I think we're going to switch it over to Mr. Marson. Okay, there we go. Better? So,
We're going to switch back and forth. Can everyone hear me?
Okay.
Okay. So welcome to the AFM session. I'll try to very briefly show you what AFM is about, and we're going to look at a butterfly wing. But first, Angela, did you get that butterfly wing?
Let me show it. Let me show it right now. So Marcy.
All right. So hold on a second. Let me just do a very quick intro, and then you can show it.
Got it.
So you guys probably learned something about AFM. I hope so far.
We did the magnet activity.
Okay. Well, it's a scanning probe technique. So it is a microscope, but it's not a microscope that would focus anything or use any kind of light or electrons. Instead, it uses a probe, and that probe touches the surface or comes within a very close distance, so it can feel atomic interactions from the surface. That probe is very, very sharp. Let me show you what I mean. So I pulled up some images over here. So this is a chip that's held in the tweezers. It's about 3 millimeters long, okay? At the end of that chip, you have a cantilever. So this cantilever at the end of the chip is already smaller than a human hair. And now on top of that, rather on the bottom of that cantilever, you're gonna have a tip with an apex. And that tip is etched out of silicon usually to a very, very sharp point. It's not necessarily spherical. It usually looks like a little pyramid, but it is edged to a super sharp point, which is on the order of 4 to 5 nanometers. That's the point we're using for imaging. So this is exactly what we're going to be bringing down to the sample and what we're going to be using to touch the sample to actually see its surface. Okay? So that's what, in a nutshell, atomic force microscope does. Now, Angela is going to show you what we're going to be looking at, and then we're going to progressively get closer and closer until we get an AFM image of it.
So this is what I was talking about yesterday. Was it yesterday? It was, when we were talking about thin films and all the structural coloration, right? So we're going to take this blue Morpho butterfly. So on the left, or right here, you can really see how beautiful it is. If you've ever gone to any sort of museum, they generally have them. They're awesome to look at. And I actually bought a wing off of Etsy. I bought a few wings off of Etsy, and then I had Marson grab them and mount them onto a plate for the AFM to take a look at. But I also want to show you, just for context, what we're looking for. So, right, the structural colorization is because of this nanostructure that's going on. So the wing is made up these little like plates, I would call them, right? And then if you zoom in closer on the plates, you'll see these like little bumps here, and they're called lamella. And then if you did a cross section of that material, you can see how it's kind of the structure. And actually last night, if anyone watched The Strange World of Nanoscience, they talked about it, right, in the video, maybe, yes, no, okay. Yeah, so we're gonna take a look at that, which I think is really cool. These images here are all SEM images, like the ones that we used with Ryan, but so we're just gonna use a different method so you can kind of compare and contrast the differences, all right? So I'm gonna hand it back over to Marson.
All right, can you highlight the other video?
Yes.
I mean, the other feed?
Yes. Where are you? Oh, here. Okay.
All right. So Angela gave me the wings. I prepared them. You can see them here on the stage. That's the sample with the wing. All right. Now we're going to send it under the microscope. So my tip is mounted at the bottom of that device. This is a scanner that's actually going to be moving the tip up and down and scanning it over the surface. So we need to get within 1 millimeter. All right, I'm gonna move this thing back a little bit, and then I'm gonna share the screen from the actual instrument.
And just for context, I wanted to point out that the actual AFM is just the little like thing that's sitting inside of the box. So the box on the outside is actually to help with stabilization and any sort of vibrations.
Right, this is a floating table.
Yeah.
So this thing is isolated from the ground, and that's how we don't have any vibrations.
Oh, that's my dog, sorry. But also for context, there's a, Marston's actually in the basement of the building. So he is underground and between two buildings or under the building? Between two buildings, yes. And part of that is to isolate, again, from any sort of vibrations, because we do have big delivery trucks, you know, typically driving around, and those vibrations can impact your data taking.
So if you're thinking about becoming a scientist, that's what's going to happen. They're going to put you in a basement. All right. Let me share the screen again. So this is my control center. Oh, come on, go away. This is my control center, and over here you see this cantilever that I was talking about. So this is already installed in a machine. This is the cantilever view from the top, and then on the bottom, on the underside, that's where the tip would be. It's pointing now down towards the sample, so you can't see it. And now in navigation, you can see the surface of that butterfly wing. So that butterfly wing is made of tiny little scales, so to speak. You can see them. They're actually, some of them will move. That's why when you catch a butterfly, it's going to have this little dust that stays behind. Those are little individual scales. And then we're going to look at one of those scales. I'm going to zoom in. Okay, so this is a single scale. And as you can see, as Angela already pointed out, it's made of little lines. We're going to try to see some of the details on those lines, which are the lamella. That looks good. So now I need to just check if everything is okay.
And then for context, the view that you just saw is just the optical microscope. And now we're going to switch over to the AFM. So you kind of have to use both visualizations to actually get a sense.
Right, so it's not a very strong optical microscope. It's like a 10x magnification. It allows us to navigate and figure out where we actually want to land. But the resolution of that microscope is about, you know, the smallest feature you can see is 1 to 2 microns, so it's not that great. And now our tip is actually going to come down towards the sample until it falls within like the atomic interaction forces. So it will feel the long range and the short range atomic interactions from the sample, and that's how it's going to track the surface, by knowing exactly how far it is from individual atoms. Okay, so we landed. The system is starting to scan right away. Well, we land with a small scan size. This is just 1 micron. So we're going to make it bigger. Let's say 5 microns. Oh, no. Okay, and I'm starting to see some structures. Let's make it a little bigger, maybe 10. And you start seeing there's a pattern showing up. Okay, maybe 20.
And yeah, you'll see the cantilever moving back and forth across the surface down in the lower left-hand corner. Yeah.
So the cantilever is scanning across this scale. And for every line that it makes, we get a 1 line on the image.
Yeah, so just like, remember the magnet demo, we're basically doing the same thing. It's the same model. Yeah.
So I'm going to start again from the top, and we'll see what we get out of this. We're adjusting some parameters. I'm not going to get into the details of this because this requires a little more AFM training, but basically we're setting up how much force we want to feel from the surface. If we set it too low, we're going to be too far, we're not going to feel it. If we set it too high, we're actually going to be hitting the sample too hard and we're going to destroy our tip, which is very sharp, but also very fragile. And then some of the other parameters are the gains. We use the feedback loop to actually allow us to track the surface, and that feedback loop also needs to be optimized a little. So that's it. And you can already see a very similar pattern than what we've seen on the pictures.
So Amrit had a good question. What is the probe made out of? Or what?
Historically, long time ago, people used to make probes out of like super sharp shards of glass. And you would have to be really, really good with micromanipulation to attach it to a steel cantilever and then put some foil on the back to reflect the laser. Now they're all made in a semiconductor facility. So they're all made of silicon through like a micromachining process. So depending on whether it's stiff or soft, it's made either of silicon or silicon nitride, but this is all made just like the microchips in a similar fashion.
And one thing I wanted to mention is that the advantage of the AFM, it's really just force. So right, with the electron microscope, some of the, basically what Ryan was alluding to is that if you bombard a sample that is non-conductive, it will sort of charge up, kind of like, when you get static cling, or you get a static shock. That just means you've been charged up with too many electrons, and then it will not look great. But so under the or won't feel great. But under the microscope, it will look weird because there's basically a cloud of electrons stuck on the surface of the sample. With AFM, you don't have that. You can just basically feel the sample. But you can do other methods. There's all different types of force when it comes to AFM, which is why it's a really versatile thing, because you can actually look at cells even, depending on you have to pick the right probe.
So think about AFM as having a little nanometer-sized finger that you can actually stick into things and actually touch them. And in some cases, you can coat that finger with a metal, and then you can have a conductive probe. So you can do nanoscale electrical measurements as well. We do those all the time on different devices. You can look at biological samples. You can look at material science. You can get the stiffness of materials on a nanoscale. The beauty of AFM is really its height resolution. So for example, I can show you while this is scanning, I can show you an image. A lot of my users work with what's known as 2D materials, which are tiny little flakes, usually triangular flakes of things like tungsten disulfide, tungsten diselenide, graphene, things like that. So here's one of my users has an exfoliated flake sitting on a substrate. And I took a cross-section across the step here on the right, and you can see that this step is 0.6 nanometers. It's 6 angstrom step. So this is a single atomic layer of this material. This is molybdenum disulfide. So this is one of the strengths of AFM. Here you have some other material science students looking at how you can layer those different 2D materials. So you have a single atomic layer over here. Now you have a single atomic layer on top of it. So over here you have dual layers. You can stack them together, make devices. Here's another one. You can also look for contaminants, which are those bubbles. But like I said, you can also look at organic materials. With Angela, we did a demo for high school students in January, and they wanted to see praying mantis eyes. And so I should have a picture somewhere here. Where is that? Here it is. So this is how it looked in the optical microscope. And then we can look at it and actually start looking and analyzing the surface with the AFM. Unfortunately, it was very soft and there was nothing really of interest except for very low roughness. But this was the AFM image that we got from the praying mantis eye. And these are the scales of yet another butterfly. So this is not the blue Morpho. This was, we don't know what it is. It was called a practice wing. But it has a completely different structure with a lot of little connections which are irregular and a very long rounded scales on top.
Marcin, can you put the the one that we took the other day, can you put it side by side so they can have an idea? Yeah, so you can see the one on the left is the blue Morpho, and the one on the right is that practice wing that Marcin was talking about. So I thought that was really interesting.
So the practice wing has a lot of little connections, but completely different large-scale structure of the ribs. Blue Morpho has a very fine ribs, very sharp ribs, and a very regular structure, like a ladder of those connections in between. And this very precise structure is what actually gives it the blue color. This is how it amplifies only a certain wavelength of light.
What determines the color?
So the color, light is made of photons, and each of those photons usually is going to have a certain energy. So the energy of the photon is related to its wavelength of oscillation, and that's what gives it the color.
That was, I guess, the question. It depends also on its thickness.
The size of
That's
the material.
okay.
Just like thin film. Yeah.
Right.
So
Okay, that's what I was wondering about on the second one, because it's red and then orange, yellow.
Oh, the colors of the Marcin, why is it colored on the AFM image? I think is
so I'm sorry, should have covered this earlier on. The color is simply a color coding for the heights. So when we look at a 2D image, we want to see what's high and what's low because it's a three-dimensional data set. So it's color coded here with the dark being the low parts and the bright being the high parts. But this is completely arbitrary, and we can select whatever color coding we want on it.
So it's just like the electron microscope too, where it's really just detecting a signal. So it just has, lots of signal, not a lot of signal. But the color, what I think is cool about the color is this is the trademark AFM color, because it's, but what is it? The Santa Barbara sunset, because that's where
Number 12.
Yeah.
Santa Barbara sunset.
Yeah.
But I can put a color on it that will be more familiar, something like something that goes all the way to yellow. Not this. Let's just say this one. And you can think of it like a topographical map when you look at a map of the mountains. And you're going to see the valleys being deep green, and then the mountains start getting yellow, and then the tips of the mountains are red, right? So this is the same kind of color coding. You're going to see one color on the lows, one color on the highs. But you can also display your image in 3 dimensions, in which case you actually see what's high and what's low. Does that make sense?
Yes, you got a thumbs up. Okay, I have a couple more questions. So is the silicon one of the materials used as a vehicle, like in yesterday's talk? So silicon, in this particular case, is being used as a tool, not necessarily a vehicle. Yesterday in Cody's talk, Cody used silicon as a substrate, and then the nanoparticles were the vehicle that held the palladium atoms. So it's a little bit different. But silicon is honestly used quite a lot when it comes to research because it's relatively cheap, it's abundant, it's a semiconductor, which means that's why a lot of the devices that we use, we can dope it into making it conduct electricity or not conduct electricity. So it's a really useful material. And then Amrit also had a good question. If you were able to make enough of the practice wing to the macroscopic level, wouldn't it emit the same blue color? So I would say no, because if you remember, the wing is actually black and brown. That might just be the color of the wing itself, whereas this is structural colorization. So it's really because of the structure, the perfect structure, it's kind of Goldilocks again, the right structure, the right size and scale to really emit that one blue color. Whereas the other wing, frankly, one, we don't really know too much about that particular wing because it was just some random wing that we got sent to play around with. But we wanted to show just for contrast. I think because it's so big and then so small, the shape and structure, that it doesn't have the sort of Goldilocks just right fit for it to emit that blue color. Yeah.
So you can think about it. You have those lamella and they have a certain distance between them, right? Especially the vertical stripes that we don't really see here, but Angela showed in the SEM images. Now you get all kinds of wavelengths coming in there because that's the sunlight that's coming in. But only wavelength that can fit particularly between this lamella and get amplified, that's the one that you're actually going to see coming out. And everything else is just going to disappear.
Mm-hmm.
So if you change the spacing between those lamella, you would change the color.
Mm-hmm. Okay, Dustin has one question. How much further can this AFM zoom in?
So this is not the best sample for that, but let's give it a try. So the AFM resolution is really limited by the size of that tip. So very often if we get like a crystalline sample, we can see single atoms in that sample. I'm gonna slowly zoom into 2 microns just to get an idea where we are over here.
Oh, and Dustin has another good question. How do you feel an atom? What are you feeling?
So there's 2 things. One thing is atoms have electrons, right? So those electrons create a charge around them. So you do have short-range Coulombic repulsive interactions. So if you bring 2 atoms together, they're going to start pushing against each other, right? So this is the repulsive force. That one is a very short-range force, but it's a very strong force. So as we bring the atoms closer between the tip and a sample, I mean, in reality, no 2 atoms can ever touch. So as we get them closer and closer, there's more and more force between them, pushing them apart. And we can feel that with this cantilever. The cantilever bends. We have a very high precision of measuring the force on that cantilever. But you also have long-range attractive interactions. So as the tip comes closer, there's the long-range van der Waals interactions where the 2 atoms actually try to get together a little closer. And that interaction pulls the tip down when it's far away from the surface. And when you're dealing with samples that are very, very fragile and delicate, you can actually use that force to run the AFM, where you don't make any contact with the sample, but you try to maintain that pulling force and use that to image how it changes across the sample surface. So those are the forces that AFM will feel. All right, so we got a little closer. Let's get a little closer still and see this little staircase, what this might be.
Sometimes the way I envision the feeling of the atom, it's kind of like, if you close your eyes and someone entered the room, you would kind of sense their presence almost. I don't know. I like using that analogy. I don't know, too wild, but yeah.
Okay, so now we're scanning a 0.5 micron frame, and once it scans a couple lines, we'll see that there's actually little steps in it. So we're looking at the edges. Now, of what exactly? Let's see, so this was our image. So I zoomed in, I believe, on this. And we're starting to see, this is just gonna be a digital zoom, so it's gonna get pixelated. But we're starting to see the little steps that are here on the side. And also here coming from the top. So I think that's what I'm looking at over here. The distance between these steps is about 150 nanometers. So if we go back to our analysis, that's going to be about, yeah, this much. Yep, so those are the steps that we're seeing. Kind of matches.
Does anyone have any other questions for Marcin while we have him?
You can see now that we're imaging this less than a micron. The tip is barely moving over there.
Yeah.
That's
Amrit
the range for imaging.
Amrit says this is blowing my mind in a good way. Yeah.
So it is actually, when you're looking at this structure that we're seeing right now, it is actually looking along the edge of one of those single little ribs in the picture. But unlike the SEM, the sample is not coated with anything. There's no vacuum involved. I don't have to worry about charging. I just stick it in there.
Yeah. Okay, another question from Karitika. How many samples can you usually analyze with one tip before you have to change it?
Yeah, that's a difficult question. So tips are considered consumables in AFM. They get used up. How many samples you can image with one will really depend on the sample and on the operator. If your sample is clean and not very aggressive, so some kind of a flat surface made of a very smooth material, not too hard, you can image 100, 200, 300 images if you're very careful. But if you're imaging biological materials, your tip very often is going to get contaminated. Something's going to get stuck to it, and then it's very difficult to clean. When you're imaging things with big steps, then it's very hard to maintain very low force, because as the AFM steps like 2 microns up, 2 microns down, it's going to crash inevitably, and that tip is going to get ruined. If you're imaging hard materials like ceramics or titanium or quartz, they actually grind down that silicon tip a little bit during imaging. So it really depends what you're doing. Sometimes as little as 1 image, sometimes as many as a couple hundred, and then anywhere in between. The probes are also not too expensive. What we're using over here is about $20. That's how much a single probe costs. Some of the more fancy probes that have designed tips coated with like special diamond-like carbon coating for hardness or artificially sharpened or something like this, they cost about $100 each, $120 each. So those you're a little more careful with. But at the end of the day, the probes will be consumable.
How much does this tool cost, Marcin? So the SEM the other day, or just now, was $500,000. How much is this one?
Oh, well, in that case, AFM is a bargain, only $150. The simple research grade AFMs, even the very good ones, usually top out at about $300,000. But there are very fancy AFMs with robots inside that are used for semiconductor manufacturing. Those are the ones that can like handle their own probe exchangers, sample exchanges, automatically navigate to the right places. And those cost about $1.5 million. But those are essentially hands-free production AFMs. You just give it a cassette full of wafers with structures on it, and it will load the wafer, find the structure, image it, and spit out the result.
Great.
We don't use those.
We can't afford those.
We can't afford those.
Yeah. All right. Well, if there are no more questions, we will thank Marcin for his time and energy for dealing with some bugs. I always ask Marcin to play with the bugs, and I don't know if he likes it or not, but.
Yeah, we have some ugly pictures of different bugs too. See, bugs for Angie. That's what I do.
Yeah, I have a whole folder dedicated.
Yeah, some other eye that was leaking stuff.
Yeah.
Some scales of a different, I think this one was some kind of a fly that we're trying to look at.
Oh, Amrit wants to know, have you done a snake?
I have not done a snake, no.
Not yet. If you send us a sample, we can try.
No, one of the weirdest things I've done was chocolate.
Anybody else? How did the chocolate look?
It just looked like a polymer, essentially.
Not very.
Kind of a smooth surface with the little grains in it.
Probably grains of chocolate and little bubbles, because sometimes the chocolate's aerated. Yeah.
Maybe, I don't know.
All right. Anything else? Anyone else?
I just wanted to show my bug collection here real quick.
Ah!
Oh, cool.
Nice. That's great.
Looks like a box of samples that Angela brings me every time.
Yep.
Yeah, the sample. So the one. So just to explain myself is, we had a school, a really remote school called Indian Digging School. They came all the way. It's like a one-room schoolhouse kind of thing. It was crazy, but they live in a very rural area, and they were collecting all these bugs. And they had mailed me a sample. And they mailed me the sample. It looked like a nightmare. There were like crazy giant bugs, crazy small bugs. So we put them into this AFM and one of the SEMs that we had, and it was really cool to see, but it was also slightly terrifying. So, yeah. All right. Well, I think that about does it for us. I think we'll switch gears. I think we have Miss Jenny up next. Let me double check before I say that. Yes, we have Jenny. Jenny, are you good to go?
I am. I'm just wondering if anybody wants a quick stretch break first.
Yeah, we can do that. Maybe like a 1-2 minute stretch, bend, and snap. I don't know. Remember Legally Blonde? That was a callback. Okay. All right. Let's do like a 1 minute stretch break. And then, yeah, or a chocolate break. Very good. But yeah, thanks again, Marcin. I really appreciate it.
You're welcome, guys. Let me know if you have more questions later. Angela can send me an email.
I do. Dustin has a quick question. Are you rendering a higher zoom picture now?
I'm trying, yeah. I've gone down to 250 nanometers. I'm trying to see if I can get any roughness, any texture out of it.
So I will share those images with you guys too, so you can grab them and take a look. I'll also share the bug pictures too. So yeah. All right. So quick little stretch break, and then we'll be back with Jenny.
All right.
Okay.
Bye, guys.
So yeah, we'll start again at 41, basically. Bye.